communication. All right, so as you can see from my title, there's a lot of buzzwords there. You know, I'm going to be spanning computation, inference, and economic perspectives. The last century, these were some of the focus areas of many people in mathematics and related fields, and they got somewhat separated. And I think the current era is notable for bringing them back together. And so that's what I want to accomplish in my talk. I'll have a little bit of history, but really fairly quickly try to turn to modern research problems and you know, actual techniques and results and then consequences of what those are. I do want to emphasize the economic side of what we're talking about. There's a tendency people in computer science and statistics, where I've kind of spanned, to not pay too much attention to you know, economics and multi-agent and game theory sort of considerations. I think that era is vanished, is over now, and so this talk will hopefully simplify that. All right, so yes, my field, machine learning, is much in the headlines, and I want to say a little bit of philosophy of what I think is happening, why it's in the headlines, and where it should go. So to say something about that, let me first of all emphasize that there are at least two sides to machine learning. The pattern recognition side has been the focus of a great deal of work in the last 10 years. And so what you've read about in the newspapers or seen talks about is often on pattern recognition. It's become a commodity. There are platforms you can download and build a business around pattern recognition. And roughly speaking, it's gathering large amounts of data, typically labeled data, and you know, finding patterns in that data, finding replicable patterns, and finding being able to make predictions. I'm going to emphasize in this talk that there's really a whole other side of machine learning that has to do with decision making, and particularly when it starts to become high stakes decisions in the real world, not merely online decision making. When there needs to be explanations and transparency, when there are multiple agents involved, and in fact even markets. So I'll get there. Let me not belabor that on this slide. Let me start off a little bit with this slide. Kind of this terminology, not just in machine learning, but AI has very much been in the news, and I want to say a little bit about that. AI has come to sort of be used for anything in technology that has data or algorithms in it, and I think that's somewhat unfortunate. The original terminology was kind of Turing and McCarthy, thinking about it almost as a philosophical aspiration. How could you put thought in a computer? And that still hasn't happened. We don't have thought in a computer. We have large data sets, and we have pattern recognition devices that extract predictions from that data. That's not the same as thought. What's really happened in the last few decades since McCarthy, the dominant trend in industry uses of computers and data has been for what we might call intelligence augmentation. In fact, Doug Engelbart, shown there in the 1960s, pushed this really as an alternative to the McCarthy perspective. So search engines, recommendation systems, natural language translation. These are computer programs that use data, and they find patterns that help people be more intelligent. So a search engine is not itself arguably intelligent, but it helps us to be more intelligent, arguably. And similarly with recommendation systems and even natural language translation. The computer's not understanding language, it's sort of mapping between strings, and that helps us to be more communicative. I'm going to argue that there's a third perspective emerging, which is really kind of neither of the above. Let's call it, just have a name, intelligent infrastructure. And this is really the perspective, if you will, of Internet of Things. But Internet of Things was mostly focused on the computer science centric problem of getting things on the internet, just having IP addresses for everything in sight. But it's really broader than that. It's having intelligence coming out of the web of connected devices. It's transportation, dwellings, planning, and it's interaction with human beings. So it's about people's values, about decision making in the real world. It's about uncertainty, and putting together visions of the world via little pieces. So far beyond the Internet of Things, but it's really what's happening in the real world. We certainly have devices everywhere, and they are transmitting data, and there's an attempt to aggregate that and to help our own decision making as humans. All right, so let me say a little bit more about decisions. That was kind of the broader perspective on the kind of engineering field that we're trying to build right now. It's not just about imitating humans, it's about building bigger systems that somehow span vast numbers of people and span the entire planet. But let's return now to a single person and think about a decision-making process, which is part of the overall tapestry of this intelligent infrastructure. So imagine you're sitting in the doctor's office in a couple of years, and the doctor gathers all kind of information about you, your blood pressure, your height, your weight, and even your genome, and so on. And imagine 100,000 numbers have been measured about you in that moment, and those numbers go into the world's biggest machine learning, medical informatics system. So it's been trained on all the world's medical data, and it's some big deep learning system. And its job is to make predictions. So it's going to make predictions based on all the historical data that have been assembled. And maybe it makes for you a prediction that you're about ready to have a heart attack. And what a prediction is, of course, is some number that's over some threshold. So the threshold might be 0.7 based on historical data. Your number might be 0.701. And so, you're licensed to wonder whether that should be thought of as a decision in any sense. And I would argue no. If that happens to you, first of all, you're going to ask about uncertainty. You're going to say, well, what's the error bar on that? Am I just a little bit over it, or am I really clearly over the threshold? And error bar doesn't mean just a classical little Gaussian error or something. It reflects all the uncertainty about where the data came from, how old the data, how stale the data is. Was the data collected on relevant people like me, or different people? Was it collected on different machines 10 years ago, 5 years ago, 1 year ago, and so on? All those factors need to go into calculating an error bar. And so this is really almost a database kind of question about provenance of data, but it's much, much richer. It's relevance of data, and it's how that goes into what uncertainty you have about even a simple thresholding procedure. All right. Now, as you start to think that through, and the doctor explains the uncertainty, you're going to start to have a dialogue. It's not going to be over then. You're going to say, well, wait a minute, I forgot that when I was a kid, I had asthma, and that's maybe that affected this. Or my parents did this or that. And you may ask what if questions. What if I were to exercise more or change my diet and so on? So what you're doing in that moment is you're actually bringing new data to bear that wasn't in the original data set. It couldn't have been. You can't have all possible data. And around any decision, that's always going to happen. There's going to be new data, which didn't seem relevant before, but now it's suddenly highly relevant. And that's real decision making. And so you're now going to bring that data and you're going to analyze it with your doctor kind of in the moment. You're going to have a discussion. You're going to ask what if questions, meaning talking about data that you didn't really have but you could have had, and how that might impact the situation. So real decision making is this dialogue, really kind of a statistically oriented dialogue. And we're not seeing really any of that in modern prediction systems. These big neural nets that make spit out things that look impressive are not really doing this kind of decision making that we really need to be able to support real human consequential decision making. Now it's not only just one decision making, one decision. It's in my own life today, I'm making many decisions, and they're related in various complex ways, and they're at different time scales, and so on and so forth. And all of you are doing that, and all of us are interlinked in our decision making. Certainly with things like healthcare, what happens to me depends on what happened to you yesterday, and so on and so forth. So it's across a network. It's across a network over time, and I don't mean just over like milliseconds. It's over years where consequential decisions are being made, and moreover, it's decisions when there's scarcity and competition. And now we move into the real world of not just virtual world, what's on the computer. It's, I want to make a decision to go from point A to point B. Well, as I do that, I create a little bit of traffic. And if you do the same thing, you create even more traffic. And we start to interact as people make decisions in the real world. And so that brings in the economic perspective. All right. So let's kind of be, little even more explicit about this and consider classical recommendation systems. This is a part of the pattern recognition side of machine learning. It's a simple kind of idea, and you all know what it is. If you go to Amazon or some site like that, a commerce site, you will make a few purchases, and then it'll start recommending other purchases to you. And it's doing that obviously on the basis of data. It has other people like you that have been on the site, and it'll use that data to make recommendations for you. So it's really pretty simple, and it's a kind of a matrix factorization problem. It's just machine learning, a successful version of machine learning. And in fact, billion-dollar industries have built on these simple recommendation systems. But they're only pattern recognition systems, and that's a problem. That means that they can't be used safely, without consequences in lots of real-world domains. So in particular, consider recommending movies. That was kind of the original use of recommendation systems. And if everybody starts to use your app, you may recommend the same movie to 100,000 people because it's a good movie and everyone seems like they might like it. And that's not a problem because you can copy the movie as much as you want. You can copy the bits. You don't have scarcity in the virtual world. Similarly with books, you can copy the book as many times as you want nowadays. But as soon as you start to recommend things in the real world, you start to run into problems. So if you recommend restaurants, you have an app that recommends restaurants to people in some city. And if a very small number of people are using the app, it's not a problem. But as soon as everyone in the city starts to use it, you can easily recommend the same restaurant to 10,000 people. And now you've created congestion. You've filled up the restaurant. People are going to go there and there'll be a line down the street. And now you have to think about how you're going to fix that. And I think this is kind of where Silicon Valley gets it wrong. They think somehow that they're going to know a lot about you when they make the recommendations, and they're going to make the recommendations you really, really want. So they know a lot about you. Why? Well, because they have your browsing history and they're good at showing ads to you that you like and so on. They think, of course, they're not really very good at it. And so they're going to recommend to you, well, you probably want to go to this restaurant. They're going to do the load balancing themselves. And of course, that's kind of, obviously not very economically sound. You're not going to know enough about me to know what restaurant I want to go to at any given moment. I may change my mind. I may think about new things. And that's what decision making is, again, like it's in the moment. It's thinking about things you had never thought about before to make your decisions. And so there's no way that someone in Silicon Valley could know what you most want. So what you really want in this moment is to have your decision making taking place in the context of a market. And there's going to be bidding going back and forth, and there's going to be data analysis that supports that market. So in that sense, it's going to be new from, compared to microeconomics and game theory of the past, which was based on assumptions that you knew the preferences a priori. We're not going to have those assumptions anymore, but we still have to have this kind of interactive auction or bid kind of framework so we can start to load balance effectively. Same thing with just recommending streets to drivers. If everyone is using an app that recommends paths to the airport, then you're going to send too many people down the same street, and now you shouldn't be the one deciding who to send down which street. You should be giving people options, and they may have some payments. If you want to go down the fastest route, you have to pay a little extra today, and maybe you realize, well, no, I'm not in such a hurry. I could save my money for some other day. So you have to start to build up a little market where on one side of the market you have the drivers, and the other side you have the resource, in this case the street segments, and you have bids going back and forth between them in some hopefully very flexible, non-intrusive sense. Okay, so in fact, instead of thinking about this as just a pattern recognition problem that needs to be fixed if you don't do load balancing, you should think about it's creating a market. You have producers on one side, consumers on the other, restaurants and diners, street segments and drivers, and so on. And you need to match them up in some healthy, economically sound way that gives, a good equilibrium, that gives good value to both sides of the market. And so this isn't just classical microeconomics. We're using things like recommendation systems. If I go into a city and I want to go to a restaurant, I can't have had experience of all the restaurants before. I can't have a preference ordering over restaurants. The only way I can go is that there's some history about what kind of restaurants I seem to like. And the system knows a little bit about me to help me hone in on a subset, or maybe there's a recommendation system based on friends, and there needs to be information flow that supports a good two-way market. All right, so I hope you can sort of see that there's going to now be new algorithmic challenges emerging here, and kind of learning meets economics is really going to be becoming a thing. And in fact, this is not entirely new perspective at all. Certainly, markets have been thought of as algorithms before. They're decentralized. They do complex things like bringing food into a city day in and day out. And they do it with little local decisions that don't require a lot of intelligence on the part of the participants. They're adaptive, they're robust, they're scalable, they can work for hundreds or thousands of years, and they can work at all kinds of scales. So if you were sitting up on Mars looking down the Earth, you'd be excused to think about that mechanism that brings food into a city, whatever that network is. It's intelligent. It's a living, breathing piece of intelligence, just like a brain is intelligent. And you can understand a little bit about its intelligence. That's called microeconomics, and we know a lot less about the brain. So returning to this AI argument, AI viewed as imitating human beings has got a lot of problems with it. First of all, we don't have much clue about how human brains work and human minds work. It's going to be a long, long time. Second, we have a lot of clue about other kinds of intelligences. And moreover, building these big network intelligences is going to require computers to be complementary to humans, to do things that humans don't do well, to make the overall economy work well. And that's very different from trying to imitate humans and to surpass humans in various kinds of tasks, which is unfortunately where the current kind of trends in AI have gone. All right, so that's enough philosophy. Hopefully you found that useful and interesting to kind of get a little bit of a mindset. And what I want to do in the rest of the talk is start talking about the engineering and mathematical and computer science challenges that emerge as you start to think in this way. And so there's lots of easy problems to write down and start to working on the interface of machine learning and economics. And by machine learning, I really mean computer science meets statistics. So we kind of have three fields participating here. So multi-way markets in which you learn by exploration. That's new from an econ point of view. Multi-way markets in which you have recommendation systems. That's also a new notion. Strategic classification. We'll talk about that a little bit in a moment. Auctions where you learn preferences. Price-based mechanisms to help you distribute and have decentralized algorithms, and then various trade-offs, between things like privacy, risk, and computation. None of this is entirely new. There are indeed papers on each one of these sort of things, but it's definitely not emerged as a whole area of inquiry of its own. And relative to the other side of machine learning, it's tiny.
Michael?
Yes?
You're about to run out of juice in your computer. You know that?
I do know that. I thank you for telling me. I saw the red there. So,
Okay.
boy, really, someone's able to snoop onto my computer and know that I'm out of juice. That's fun. But it's a friend. It's Alicia, who I know well, so that's fine. Yeah, actually, let me now that we've had that break, that's a good time to in fact solve that problem. Okay. The other point I want to make about AI before I move on to recent research is that AI researchers tend to aim at two things. One is intelligence. We're going to have intelligence in the computer, and I kind of hope you agree that that's not a well-formed problem. At least as I've alluded to, markets are intelligent, and there could be other kinds of intelligence. It's not really clear what that really means. And the other one is autonomy, that we should have our machines be autonomous. And kind of the reason is that's what Turing originally asked for, or McCarthy, that the machine should sit there, you should be able to interact with it, and it should respond autonomously. It doesn't need help. And that's fine as a philosophical aspiration, but it's not fine if you start to roll these things out in the real world. We don't want machines to be autonomous. Like, in the air traffic control system, if every plane was completely autonomous, that would be disaster. We want machines to interact with the fabric of other machines and with us. There should be interaction. They should be definitely not autonomous. All right, so we'll talk about that a little bit further as we go. But this economic perspective definitely militates against pure autonomy. It really wants to have things be integrated in. Okay, so let me give you some ideas, some sense of some projects that I've been working in my group. I've selected 4 out of a bunch of others over the last decade to give a little bit of flavor of what kind of research you can do here. It's mathematically interesting and has impact in the real world. So we'll talk a little bit about bandits, and we'll talk about strategic classification, auctions, and equilibria. So let me start with a project that's kind of a nice, simple juxtaposition of economics ideas with learning and statistics ideas. So this is with Lydia Liu, Horia Mania, students with me at Berkeley. So we're going to put together competing bandits. Bandits are kind of a core idea in machine learning and statistics. It's about not knowing what's the right action to do and having to explore to find that action. And then matching markets is a core idea in mechanism design economics. There's been Nobel Prizes for matching markets, matching kidney markets, or matching colleges to applicants, and so on and so forth. All right, so here's a little picture of a multi-arm bandit setting. I have an agent on the left who's trying to make a decision among 3 options. They don't know which of the options gives you the higher reward. And reward is stochastic, so there's some distribution of rewards for each of these arms. And so you try them out. You try out arm 1 and you get back a reward. That's one sample out of a whole distribution. And what you'd like to do is pick the arm that has got the highest average reward. Okay, so one sample is not enough to let you know what the mean reward is. So you will have to probably try it a few times. But in the meantime, you better try some of the other arms as well. So you maybe try arm 2, you get a reward, and so on. So how do you allocate your exploratory behavior here to find good arms? But at the same time, you want to start picking the good arm more and more, so you actually get rewards and you exploit. And so this trade-off can be managed with a number of really neat algorithms. One that I can explain really easily is the UCB algorithm, upper confidence bound. And all it does is it takes the data from each arm and it maintains a confidence interval for the mean reward. And so the confidence interval is typically done with something like a Hooftine bound. It's a large deviation confidence bound. And the algorithm can easily do this after collecting data on each arm and updating these confidence bounds. And the way the algorithm works is that it looks at each round at the upper confidence bound. It looks at the upper side of the confidence bound, and it takes the arm that has got the highest upper confidence bounds. So here that would be arm 2. And why is that a good idea? Well, it's a good idea if the actual distribution is shifted over to the right, the mean reward is high, you should pick that arm because you're going to exploit, you're going to get a good reward. But it's also a good idea if you have a big uncertainty. That upper confidence bound might be big because you have a lot of uncertainty. And so you should pick that arm because it has high uncertainty and maybe reduce the uncertainty and then not pick the arm so much in the future. So two ideas inside of one algorithm here, just pick the upper confidence bound and you both explore and you exploit. And the mathematical analysis here is a interesting thing to go through. You will find that you can converge quickly to the best arm. And this is typically measured in terms of something called regret. Regret is comparing your performance to an oracle. The oracle is assumed to know the optimal arm a priori. So maybe arm 1 is the optimal arm. The oracle knows that, and it just selects arm 1 on every step. All right. Relative to that performance, how good is your performance? That difference is called the regret. And regret should not grow linearly. That shows you're not learning anything at all. It should grow sublinearly. And so a typical regret might be square root of time, or ideally even better, logarithmic in time. All right. And so this turns out this UCB algorithm is logarithmic under certain assumptions. All right, so that was the learning side of the story. Now let's talk about matching markets on the economic side of the story. So we have a two-way market here. We have buyers on one side, sellers on the other. And in the classical literature, you assume that you have preferences a priori. So the buyers, the first buyer prefers arm or seller 1 to seller 3 and prefers 3 to 2. And you write down this list of preferences for all buyers, and you similarly on the seller side. Okay, so applicants to college have to write down a list of which colleges they prefer, and the colleges have to prefer the applicants in some ordering. And given the lists of preferences, then their algorithms, for example, the famous Gale-Shapley algorithm, deferred acceptance, finds a matching that has got a nice property. It's an equilibrium property. It says that you can't find any pair who would be happier with each other than with their current assignment, because that would be an unstable situation. Okay, so this is great, but of course it runs aground if you have situations with large numbers of agents and large numbers of sellers, or just where there's any uncertainty really. Because so if I go, I might be able to give a listing of colleges and give my preference, but even that's quite hard. But I don't have a preference on books or on restaurants in Shanghai. I have to collect data. I have to maybe use other data from other people, and I have to have a system in which that kind of preferences are being adapted and learned and shared. And so as soon as you go to that, you're in the statistics world, and you're at kind of the classical microeconomics world. All right, so what if we put the two together? What if we have matching markets meet bandit learning? And so the picture, I think, will convey the idea. I'm going to have now two agents, and both of them are exploring their options. And so they pick these arms and they get a reward, but we need to have some notion of scarcity, that I can't give the same arm to both agents. All right, so what if both agents pick arm 2? Well, in our model, what we're going to assume is that agent 2 has a preference back on the agents. Arm 2 has a preference back on the agents. And in particular, maybe arm 2 prefers the bear. So the bear gets the reward and the human got no reward at all. All right. Now the human observes this and the human says, well, I liked arm 2. It was looking pretty good. But I see that if I pick arm 2, the bear also seems to like arm 2 and I lose. So I better start hedging my bets and pick some of the other arms more than I otherwise would. And that more than I otherwise would statement suggests there's going to be more regret for that agent. They're going to have to explore more and have more regret for not, knowing the optimal arm a priori. So we need to then do the mathematics to figure out what that regret is and quantify that in terms of the various parameters. So we've done that, and we have published now papers on this notion of a bandit market. We have agents on one side, arms on the other, and you get noisy rewards. You learn your preferences and you interact with other agents. All right, and so here is the notion of regret. I'm not going to get into details at this point. There are papers on this if you want to look into the details. But again, you have to have an oracle. You have to have some thing you're comparing to. And for us, the oracle is, what if I did know my preferences a priori and some oracle took those preferences and gave them to the Gale-Shapley algorithm that would form a matching. What if I just fix that from the beginning? How well do I do relative to that? So that we call it the stable regret. Okay, so we compare our rewards to the stable, the mean reward of a stable match. All right, and so then we start to analyze algorithms specifically. Here's one that we've analyzed. We call it Gale-Shapley UCB. All it does is it forms those confidence intervals like we were showing before. And instead of just picking an arm, it gives the confidence interval, the upper bound of the confidence interval, to the Gale-Shapley algorithm. Gale-Shapley takes that in and runs a match, a deferred acceptance on the upper confidence bounds, and then delivers back a suggested choice for each of the agents. Of course, if we're going to be economists, we have to say that, well, the suggested maybe not will not be followed, or we do have incentive compatibility, and we do, it turns out. All right, so long story short, we do the mathematics, and here's our regret bound. Again, I'm not going to get into too many details here, but the key is you can see it's logarithmic in n. N is the number of time steps. So we did actually get logarithmic regret. You can learn in this situation quickly. And the presence of other agents hurts you, but only in a constant. And that constant is the denominator there. So delta is the gap between my rewards and the rewards of some other agent. It's the minimum gap. So if me and the bear share the reward distributions, we're very close, have nearly the same rewards, then that number will be small, and that will give me a constant boost on the regret. But it's only a constant. We still get ergot and logarithm. Okay, so someone named Irma is typing. I don't know who you are, but you may want to mute yourself. I've noticed that coming from time to time. All right, so that was project number one. That's led to a little bit of a literature, and there's lots more things to do there. In particular, we didn't do a decentralized version of that first paper. There's also, what if I have recommendation systems blended in, and what if I prices and all kinds of things that are starting to emerge out of that first paper. That first paper is about 2 years old now. All right, so I'd like to now talk about a second project which blends economics and statistics and computer science. This is with Tiana Zernich, who's a grad student with me at Berkeley, and Eric, who was a grad student but now is a professor at Caltech, working in kind of these three departments: statistics, economics, and computer science. Okay, so strategic classification is a very interesting concept. It reflects the fact that when people are giving you data, they often care about the outcome. And they will not necessarily give you the right data because they care about the outcome. All right, so here's a little picture that suggests this. Uber drivers in Los Angeles, around the Los Angeles airport, there was a famous episode where they had come together and they realized that the prices were being set by an automatic algorithm. It was in fact a good blend of computer science and economics. And they realized that what they might do is they might collude. So at noon, they would all turn off their cell phone at the airport. And now, of course, there's no supply. And so the algorithm recognizes that. And it says, well, I better turn up the price to try to get more supply. And they leave their cell phones off for a half hour, and the price goes up and up and up. And then a half hour later, they all agree that they're allowed to turn on their cell phone again. They all turn on their cell phone and they get that really high price, and they have their ride, and they make a lot of money. This is going to happen. This is what real people do in situations where there is the possibility of strategic behavior. And Uber eventually realized this, and I don't know how they worked around it or fixed it, but this is really part of the issue. You can't just put out a system that optimizes based on people's data without taking into account the game theoretic aspects of the data collection. This is known as Goodhart's law in economics. Here's kind of a typical example. Someone defined a poverty index score, and in 1994 it looked very Gaussian, with half the people above the mean and half the people below. And then by 2003, most people looked like they were poor. And part of this was that people were now self-reporting data, and they knew what they needed to report to make themselves look poor, so they could get more benefits that way. My favorite example of this is health insurance applications. Health, companies are incentivized, of course, to try to get people who are healthy, and so they will gauge that in various ways. And one way they might gauge it is say, well, will you allow me access to data from your cell phone? And what I'm going to do is measure how much movement the cell phone goes through during the day. People who move more are probably getting more exercise. And if I measure that a little bit, it's at least one signal that helps me give you a lower insurance price. But as soon as people know that that's being done, they find ways to get around that. And there was a little device built that you could actually buy on the internet, where you put your cell phone inside the device and it moves artificially the cell phone around, and your insurance company thinks you're having a lot of exercise. All right, so is this just kind of evil and bad and we need to stamp this out? Well, maybe, but a better way to think about this is this is part of the data gathering process that we will see more and more as we take it into the real world. Okay, so we worked on this, and this is called strategic classification. And so this picture depicts the idea that you have a decision maker on the left there who's collecting data and modeling that data based on data coming from some agents. The decision maker needs to publish the model. Okay, maybe there's a legal constraint in doing that, or maybe it's just good business practice. So they send a parameter vector theta out there, kind of letting people know how the model is, what's in the model, being transparent. All right, people see that, and now they shift their data to get a result which matches more the result that they would like. All right, so that's kind of the setting. And we could model that as a game. And in particular, this is what's called a Stackelberg game. In game theory, you all know about Nash equilibria. Those are simultaneous games where multiple agents will pick an action simultaneously and you'll get a reward. Stackelberg games are where there's a sequential picking. There's a first agent who leads, picks an action, and then another agent follows, picks an action after the first agent. And now in Stackelberg games, it's quite interesting. Is it advantageous to lead or to follow? Well, actually, it depends. If you lead, you think you have more control somehow, but the other person kind of gets to wait and see what you do and then respond optimally to that. On the other hand, it's a game, so you can kind of think ahead and think of what the other agent will do. And so, it depends is basically the short answer. All right, so in this setting, we have two kinds of protocols. You can either be a leader or a follower. And so in particular, the central decision maker has two choices. They can be proactive, meaning that they update their model slower than the population. What they do is they publish their model and they wait for some time to have it stabilize, and they collect some data, and then they slowly update their model. So they let the population adapt to their model. The other way to do it is what's usually done, actually, is the central decision maker updates very quickly. They have all these computing resources, they collect data and very quickly update the model. So they are doing the best response, and the agents have to respond more slowly to that. Okay, so here's a little picture of the proactive case. The agent holds their theta vector at theta naught for several steps, and then updates it to theta 1. And during that several steps, the first capital T steps, all the agents are updating their data very, very rapidly, okay? We're able to prove that in this setting, there is a Stackelberg equilibrium, and it is one where the decision maker leads, okay? It's kind of interesting that the decision maker is leading, even though what's happening is the decision maker is holding the parameter vector for a while. But that's what happens in game theory. Things kind of get turned around. All right. Now, on the other hand, it turns out that approach can have the decision maker Stackelberg can have a high social burden. So people who really deserve a positive prediction, like in the healthcare situation or loans, actually have to pay a higher cost because of having this being the followers in the Stackelberg equilibrium. Okay. So it's worth looking at other Stackelberg equilibriums. So let's look at this reactive case. So here the reactive decision maker is updating the model faster than the population. So decision maker very quickly updates the model, and the population more slowly. Here again, we can prove that you converge to a Stackelberg equilibrium, and it's a different Stackelberg equilibrium. Okay, and actually, I got it exactly backwards. That this is the case where the Stackel or the decision maker is leading. The other one was the decision maker is following. Okay, that was wrong. Okay, so now, oops, what's happening here? Oh, okay. So there's a theorem at the bottom of this page here, which is that, just to summarize, we have two situations. The decision maker could either lead or follow. And it turns out that both of them give you equilibria of this overall system. And it turns out that the one in which the decision maker leads is actually preferable both to the decision maker and to the strategic agents. So it's kind of a real surprise that there's an equilibrium which is better for both the decision maker and for the strategic agents. All right, and that's not the Stackelberg equilibrium, which is being done currently in actual implementations of these things. And so our paper argues that this needs to change. So I had some experiments here. I think I'm going to skip through this, just showing it's a theorem. So, but just showing this in a particular case, if the model is logistic regression, and the agents at the bottom of the page are modeled as wanting to have a higher probability of being a 1, as being classified as a 1. For example, you get a loan, and there's a penalty for deviating, taking their data and moving it a little bit. Obviously, if you did that arbitrarily, you could get any answer you wanted. So we penalize the agents for deviating a little bit. And under that situation, we're able to sort of see the phenomena I referred to. Okay, so third example, and I'll have a fourth, and then I will conclude. So the third example is auctions. So this is another area of microeconomics. It's not matching, and it's not Stackelberg games. It's another area, and it's very important in the economy. There are many auctions being run all the time. Some of them are done now automatically for us behind the scenes. And auctions are, of course, a way to try to get values out of people. How much do you value something without trying to pry too much into their thinking? So you all know the kind of classical auction, the English auction of the rising price, and then you stop at some point. There's also the Vickrey auctions where you take the second price. Everyone has a sealed bid and you take a second price, and probably there's lots of beautiful theory here. In fact, Nobel Prizes for that kind of work. And then there's something called a Meyerson auction, another Nobel Prize, where you design an auction assuming the preferences of the agents a priori, or a distribution on their preferences. That's actually the typical case. That's called Bayesian. I assume I know a distribution on their preferences. And given that distribution, I can design an auction, a particular format, a way to collect bids and then to pay off people or to allocate. I can do it so that I get the maximal revenue. So that's what Meyerson did many decades ago. So this has been the standard, and it's being used widely in online auctions, ad auctions, and so on and so forth, whenever you want to maximize revenue. More and more, however, it's understood and realized that we can't assume we know the preferences a priori. We can't even assume we know the Bayesian prior on the preferences. We collect data. We see what people tend to prefer in real life, and we start to collect data. And so we should build our Meyerson auction around data collection. All right, so we've been doing this in a project with Wenchuo Guo and Manolis Zampatakis, working with me at Berkeley. And now the question becomes robustness. Because if we're collecting data from people and we're going to run our auction based on the data collection, obviously people might be incentivized to give us wrong data. And so this is kind of a problem. In statistics, you're used to having to face at least a little bit. Let's be robust. But in game theory, you have to face it. Otherwise you can't deploy the thing. All right, so anyway, the problem setting is we have auctions who are trying to obtain some information about what people value among a set of options, and we want to do this with learning from minimal amounts of data, perhaps even just one sample. So there is literature on learning from one sample. It's very promising, but it's not being deployed, and the problem is it's not robust. An adversary can come along and completely ruin the auction. Okay, so we have a paper on this now, just came out earlier this summer. And what we've been able to do is bring robust statistics ideas together with economics. So we have been able to design something we call a robust empirical Meyerson auction. So it's a Meyerson auction, but it's based on data and it's robust. And the statement, I'll give you the theorem statement, I think, on the next slide. But what it is that we say that if you are, if the distribution that you're collecting data, the distribution of data you've collected is within some factor alpha of the true distribution in Kolmogorov-Smirnov distance. That means you can add arbitrary adversarial data to the distribution up to a level alpha. If you do that, we show you still obtain optimal revenue up to a factor 1 minus alpha. Okay. So here is kind of the mathematical setup. We have some bidders. They all have a true valuation distribution, D1, D2, Dn star. But we actually get samples from a corrupted distribution, D1 tilde, D2 tilde, Dn tilde. And what we assume is that these are within a KS distance of alpha I for each of these. Okay. In that situation, we find an algorithm, which I'll mention here on the next slide, which takes samples, does some statistics, puts it in the Meyerson machinery, and gives you a revenue which is then within a factor of 1 minus the sum of all the alphas of the optimum, as if you had had the true preferences. Okay, so this is a robustness result for auctions. And we even have what's called a sample complexity bound there. It tells you how much data you need to be able to get this guarantee. And the algorithm is interesting. This is really where we're bringing in the computer science together with the econ and the statistics. It turns out that you find a particular convex envelope of a particular piecewise constant function, and you run the Meyerson auction on that envelope. So this is now a tractable algorithm using ideas from convex analysis. Okay, let me do one more example, and then I'm going to close with time for questions. So this is another project with, in this case, 4 colleagues at Berkeley, all students. Mina, Alex, and Yishin. Mina and Alex are students. Yishin's a postdoc, and Jacob's a faculty colleague. And so we're going back to bandit feedback and matching markets. I think this is really a very pregnant area for research. Matching markets exist throughout the world, and bandit feedback is a way to bring learning machinery together here. Now, the matching markets I showed you earlier are often called stable marriage. There's no prices. When you just match people to needs to suppliers to buyers, and so in a domain like kidney matching market, that's what you would want. You wouldn't want people buying kidneys. And then in the college admissions market, you wouldn't want that either. But there are lots of markets where you want to actually add prices. You want to let people start to set prices again to get out values that are maybe latent, and prices that allow you to start to get out at those values. So you can get a richer notion of matching markets when you introduce prices. All right, so with my 4 colleagues here, we've been looking at equilibria in matching markets that allow prices, but again, back in the bandit feedback setting. Okay, so we're really kind of going full microeconomics here. We have 2-sided matching platforms that want to find market outcomes and have the market clear effectively, and they're going to learn their preferences, and we're going to allow transferable utilities, meaning that we can have side prices between people who decide they want to be matched to each other. Okay, so again, Nobel Prizes have happened for things like this, Lloyd Shapley and others. All right, so the way we've approached this is we've introduced a new notion of instability. So the instability we had earlier was kind of a classical notion of instability, just kind of 2 partners which are not so happy with their current situation. This is a richer notion. It's the minimum amount the platform could subsidize agents to achieve stability. All right, so this took a while for this to emerge in our work. It took about a year, and we think it's significant. It's very similar to the kind of things you'll see in applied mathematics, like a singularity. How far you are from a singularity is kind of a notion of stability in numerical linear algebra. This happens in differential equations. So it happens in many, many fields. How far are you away from singularity is kind of a measure of stability. So that's what's happening here. It's the amount in prices in money that you would have to give to agents to be able to move to stability. All right, so that particular measure is in the paper. It has kind of a Vickrey VCG kind of flavor to it, but it's a novel little functional. We use our new stability measure now, not just to characterize markets. That would be more of just an economics projects, but we treat it as a loss function, and we actually now design algorithms, low regret algorithms that learn stable matching. So from data, we optimize this stability measure, and that's going to learn stable matchings under a market clearing situation where you're actually able to have prices. Okay. It has, again, a exploitation kind of flavor. And those come out most clearly when you look at both the primal and dual part of this problem. So I'm not getting into details here, and because it's a whole talk of its own, but just to sort of say a lot of interesting kind of mathematics is coming out here that, von Neumann would probably find familiar at some level. Primal dual ideas and bandit algorithms. This goes back to not just von Neumann, but Blackwell and others in the 40s and 50s. And in some ways, we're really returning and hopefully revitalizing some of the concepts that came out in that era. Okay, so that was my machine learning talk. I hope you find it a non-traditional machine learning talk. There was no talk about stochastic gradient descent or about AI and vision problems in robots. I hope you agree there's something here, that this is the kind of problems you're seeing in the real world with people making decisions and doing so in collections of other people, where complementary is needed, where sharing is needed, where scarcity is needed, and so on and so forth. And I see this really as an emerging really discipline, if you will. It is certainly about pattern recognition. We're not throwing that away, but it's even more importantly about decision making. And it really ties together these three fields of economics, statistics, and computer science, I think, in new ways. Economics and statistics have already been tied together for decades, really. That's econometrics. But that had somewhat limited scope. It was about measuring the economy and collecting data to measure the economy, less about designing good mechanisms. If you brought computer science together with economics, that was called algorithmic game theory. And that was about designing mechanisms and all, but there was really very little statistics in there. It was assumed that you knew things a priori. And then computer science meets statistics, that's machine learning, algorithms and kind of computational efficient algorithms for decision-making or uncertainty. Anyway, if you bring the three all together, then I think you start to get the glimmerings of a kind of a new engineering discipline that takes from all three traditions. And so, in fact, I'd like to finish with this slide here, which is that my personal view on what's happening in our era, it's certainly not the creation of superhumans in a computer. It's not the creation of AI in kind of either the dream or the fear of thought in a computer, taking over or solving all of our problems and so on and so forth. I think that it's almost tragic to me how many people have kind of bought into that, both young researchers, but also the media and even companies and venture capitalists. What I really think is happening is it's something akin to the emergence of, say, chemical engineering in the 40s and 50s. Before the 40s and 50s, you didn't have chemical engineering. It wasn't a field. You certainly had chemistry and you had fluid mechanics and so on. You even had quantum mechanics. So you could really talk about what happened with one substance coming together with another substance. And in the lab, you could pour things into test tubes and see it happening. But the idea that you could actually create a factory and have actual fluid flows at vast scales, making new kinds of products and having it be economically viable, having it be safe, having it work in reasonable timeframes, that needed a whole new style of thinking. So in the 30s and 40s, people started to build factories, and some of them were ad hoc, and some of them worked a little bit, some of them didn't work, some of them exploded, some of them created all kinds of troubles. And then in parallel, a field emerged called chemical engineering, which developed its own principles to allow you to build factories in a reasonable, safe, scalable, economically viable way. And that field is not just engineering, quote unquote. It has its own mathematical principles. The new thermodynamics ideas at scale were needed. I know less about the history of electrical engineering, but I think it's similar in spirit. Before there was electrical engineering around, say 1900, there was, electromagnetism. There was already Maxwell's equations. So in some ways, all the science was done. All right, but the idea that you would actually bring electricity across a city and into people's homes, that you would power devices, that you would start to build circuits and so on, that needed to be worked out, and new mathematical principles were needed, ideas of modularity, impedance and so on, to be able to build things like that. And those themselves were mathematical principles. So electrical engineering is a mathematical subject. It's not just engineering, quote unquote. So come forward to our current era, we have statistics, we have computer science, we have economics, and there is a tendency to say, well, we have all of our ideas. All we've got to do is just the engineering to build the platform, build software platforms. Companies will build these things and we're ready to go. We have AI. And I just think that's dead wrong. I think that what we have is very ad hoc tools that we don't really know how to put together, that when we build them, we actually build systems that don't work very well, that don't bring a lot of economic value or productivity. In fact, I don't think that we have seen a lot of economic productivity from the last wave of AI, and actually cause lots of societal problems, externalities. It's equivalent of a factory blowing up on us. So what we need is new thinking, and we really need a new engineering field to emerge, which takes the proto ideas out of these different fields, but takes an engineering mindset. And I want to say one last word about this word engineering, because interestingly, engineering has become kind of there's a negative side to the term. If I say social science, that sounds very good. If I say social engineering, that sounds terrible. If I say genome science, that sounds good. Genome engineering, not so clear. Even like mathematical science sounds good. Mathematical engineering sounds boring. And so oddly enough, even though the engineering has arguably changed our lives more than anything other thing that humans have ever done, including science, civil engineering, mechanical engineering, electrical, et cetera, have made our lives happier and safer and so on. Somehow the terminology has become deprecated. And so, statistical engineering doesn't exist. Statistical science sounds good. And I just want to argue that we should turn that around. That we should be thinking of ourselves as both scientists and mathematicians, but even more so in the service of building real world systems that bring value to people and actually work. We're going to need more people to work on that. We need to somehow prioritize and praise that effort, and take some of the stigma out of the odd stigma that's come associated with the word engineering. So I think I'm finished there. I'll stop now and be happy to have questions.
Thank you. That was a great talk. Thank you very much. So we have time for a few questions. This is a hybrid talk, so we have some attendees online and some attendees here in person, about 40 so people in the room. So I'm going to ask you to type your questions in the chat if you're online, and I will read it for the speaker. And if you're here, speak out your questions. So we can start off by the first question from online, and then we can go to the audience here. And if it's faster to just unmute yourself really quick and just say that question out loud, please do that as well. I just don't want 10 people to unmute and try to speak it at the same time.
I do see from the chat, a few people are referring to it, a red line, which was on the screen earlier. And I don't know where that red line was coming from. It's not on my computer and my slides. So it's somewhere else.
Yep, that problem has been resolved. I suppose an annotation that probably someone made, and we are
all right. Thank you for taking responsibility.
Yep, no problem. So questions.
Yes, I have a question. You said early in your talk that markets are not inefficient. I'm trying to remember the word. Imperfect maybe was the word you used.
They are, yes.
Could you say a few more words about that? Because I'm thinking like the perfect market hypothesis, right? Is that what you're thinking, or are you thinking something else?
Well, no, it's a real world concept. You talk to any economist and they'll recognize there's all kinds of problems with markets. There's oligopoly, there's monopolies, there's free riding, there's there's various ways that people cheat, there's collusions that you didn't plan for, et cetera, et cetera, et cetera. So, while a classical textbook will kind of show you supply and demand curves and everything kind of works out, a real world economist will say, no, it doesn't work out. And we don't know a lot about behavioral economics, and, real world people don't really behave like this, but nonetheless, it kind of helps us to reason about and build systems. And I think that's kind of the right spirit here. So, why do you need regulations? Why is just free fall for all markets not working? Well, because markets aren't perfect, and you do need to kind of bring in some constraints and some boundaries and some legal notions. You can't just let it be a free fall. And there are schools in economics which tend more towards one side or the other, but I would say your median economist is somewhere in the middle. At least everyone recognizes they have their flaws. Some of the flaws are just the ones I'm alluding to. They didn't collect a lot of data. They don't know the preference distribution, so they write down some Gaussian and it gives you a bad market outcome, and it's because they put in the wrong assumptions. And so as statisticians, we can kind of come in and help them and say, well, you don't have to have the right assumptions from the get-go. We'll build a more adaptive system. So we can hopefully correct some flaws but really more open up new kinds of markets. In a longer talk I give, I start talking about markets for things like music. There are lots of people, like millions of people in our country, especially like 16-year-olds in the inner city, are making music. And it's actually being streamed and listened to all around the world. It's not really appreciated how wide. I think 95% of all songs being listened to today were made by people you never heard about and were made within the last year. Okay. And the people making that are not getting paid. They're not in a market economy. It's just their songs are somehow being stolen away. The bits are being streamed, and so there's a missing market. All right. So the few rich people, a few like famous singers are getting all the money, and the people who are actually supplying a lot of the economic value are not. So that seems bizarre. And so how do you make a market there? Right. Well, you know who the suppliers and producers are. It's the people who made the music and the people listening to it. Can you create a market, a platform really that connects them? And the answer is yes, you can. And in fact, there's a company that I've had a little involvement with called United Masters, which is now signed up, I think, 500,000 musicians, and their music is being streamed to places like the NBA, and they're getting payments and so on. It's a whole new market. And that needed kind of new out of the box thinking, because you have to do with data and you have to collect things and build the market. It wasn't just a classical market. So I think going forward, in 30 years, you'll look back, there'll be all kinds of new markets that emerged in this era that were not existing before this era.
Thank you. We have a question in the chat from how does the proposed method scale with the number of agents involved in the market? Some high-level comments would be useful.
Yeah, so the papers that I referred to in this talk, I think I covered 4 topics. Those are all theory papers, and they write down every single, dimension, number of agents, number of data points, and so on. And there are trade-offs linking all of those. So we could get into specifics there on that. That said, this is part of being a good engineer and a mathematician in this field, is that you hold yourself to writing down scaling laws for all those quantities for everything you'd ever do. So some of that is very difficult. Some of it is impossible. Sometimes you have different regimes. If the number of agents is really small, it's hard, then it gets really easy. There's a mean field regime and so on. So it's hard to give a simple answer here. But just to say it's a critical part of our enterprise, which is to say, how does it scale? Now, are you sort of asking, if you're a computer scientist, you're often used to kind of thinking, well, for small problems, it's okay. Then it starts to scale worse and worse, and then it gets horrifically bad. And where are we in that regime? And sometimes the answer is actually, if you're more of a statistician, different, is that in larger limits, things get easier and things actually work better. They scale better. And even in the infinite limit, you can have an algorithm running which works in the infinite limit, which wouldn't work for 100. So in fact, some of the results here do have that kind of property. And part of it is coming from prices, because prices allow us to decouple. My preferences and your preferences might interact in some intricate way, but as soon as we set a price, we've decoupled. When we agreed on the price, none of the rest is relevant. And so prices can help you actually scale.
Thank you for elaborating. Do we have another question? I think we have time for 1 or 2 more questions.
Yes, I have a question here. So thank you, Professor Jordan, for visiting us remotely. So if I get your last slide right, it seems to me that you're proposing sort of a new engineering discipline at the intersection of 3 traditional disciplines, right? That sounded like the message here. I'm thinking about sort of the socio-economic implications of this proposal. Scholars do wonderful things, but I'm also thinking about traditionally, if you think about the marriage between computer science and statistics, that actually gives rise to extremely powerful big techs today, right? In a way, arguably, I just wonder whether this proposal of sort of bringing economics into this sort of landscape, what is the potential? Potentially, then my gut feeling is that that's going to make the big techs even more powerful. With all the computational powers they have, they can model all the things you've been modeling. I'm quite worried. I wonder what your thoughts are on that possible prospect.
I mean, it's a longer cover. I say I'm worried about lots of things. I'm worried about the rise of fascism in the United States, and I can't kind of head off all of that. But really, to me, it is about democracy, and it's returning power to individual people. And you're absolutely right. The centralizing tendencies are very dangerous. I think that AI without the economics is actually very centralizing. I think that they do gather all the resources and they model and all that, but I'm arguing against that kind of AI. Okay, if you want to build a music market, you don't have to have a lot of computers and a lot of, possess a lot. You simply have to know my songs are being listened to. At the end of the week, if I'm a musician, I like to see a dashboard of the country. I like to see every time one of my songs was listened to, a little dot. And so I discover that I'm popular in Ames, Iowa for some reason. Who knows? Because someone liked my music and told their friends. And once I discover that, that's economic value to me. I don't need a company to tell me about that or whatever. I can then go to the venue owners in Ames, Iowa, and I say, look, I'm popular in your city. They say, well, you are. Why don't you come and give a show? I come, we connect to the people who've been listening to me. I make $20,000. They take a little cut. I could do that 3 times a year. I start to have a salary. And all that discussion, there was no Facebook, there was no advertising dollars, there was no news feeds. So I really do think economics gives you the possibility of decentralizing, connecting producers and consumers directly. And then you don't have to have advertising driving anything. I think that's the horrific thing that happened, is that Google and Facebook couldn't think of any other way to make money. All right. So they said, well, we'll create an advertising market on the side. It's not directly linking producers to consumers. It's not helping social value very much, but it gives us some money and it allows us to have this free service. All right. But then they had to go the route of trying to provide more eyes for the advertising industry. And then they started to get more and more data to try to influence our decisions about that sort of thing. It became a little artificial world of its own. There's no economics in all that other than an advertising market on the side. There's no producer-consumer relationships. So no, I'm not saying this is a panacea by any means, but I'm just saying it's shockingly been missing from the IT world, the AI world, also the world of autonomous systems. I'm going to build an autonomous system inside of Google and show off how great it is. And you're going to say, well, it's not really great because you had 1,000 engineers on. I'll say, no, only 3 engineers worked on it. This desire to have autonomy tends to centralize. It tends to make a small number of people be only they can do it. Because if it was done worldwide, it's not so intelligent. The intelligence came from the humans. Think of Wikipedia. Wikipedia was done worldwide. It's an amazing artifact. It's in some sense AI but it was done by huge numbers of people. So no one would say Wikipedia is AI even. They wouldn't even say it's an autonomous intelligence, but it's got a lot of intelligence in it. And I'd argue that's a better model for us than trying to have robots at Google or, advertising agents or chat bots that know a lot about us and all that. But anyway, long story short, I think I think economics is not a discipline that tends to lead to dominance. It is actually a discipline that leads to decentralization. That's its natural tendency.
Thank you.
Thank you. There is a longer question in the chat, which talks about NFTs. Says, okay, NFTs might help musicians and the like to directly pay them. Computing is finding ways to divert economic gains, but probably we are still at the budding stage. What do you think?
Yeah, I mean, I'm fine with NFTs. I think it's just another way to add value. It creates more objects in the world that I can assign value to, and I can trade. And more trade is good. More people specializing, more complementarity, more international trade is good. All this talk of one company dominating AI is all nonsense. Really, different countries are going to do slightly things a little different. There'll be complementarity and they'll trade. That's how things will work. And NFTs just gives you more things to trade. but I don't think it's anything more than that. I don't think it is a fundamentally economically interesting per se. It's not, and you know, you don't need crypto to be able to share economic value. You know, this music example I gave you is that once I see I'm popular in Ames, Iowa, that's a fact in the world. I mean, I need someone to verify it, right? But I can show the venue owners and I can go and I can get my show. And it was no crypto needed for that. Really, it's just kind of realizing that when bits are streaming over the internet, it's not just bits. A lot of times there's actual economic value that could be associated with those things between the producer and the consumer of those bits. And if you reveal that and let them start to interact, then markets are created and good things can start to happen. Markets are creative. They'll create other ways. If I go to Ames, Iowa, I might connect, you know, someone might come to my show. I might say, anyone comes to my show, I'll pay your wedding for, you know, $10,000, you know, and so suddenly you're super excited. Your favorite musician is going to come to your wedding. You're happy. I'm happy. That's what markets do.
Thank you. And one last question, and this is, can decentralized solution achieve centralized optimality through some sort of pricing? In your point of view, what's your
yeah, I mean, that's almost a theorem, right? So there's, of course, first of all, there's not one answer to any of these questions. There's a whole field. So there's a whole notion of price of anarchy. And in algorithmic game theory, which is a very broad notion. And what it does is it compares the optimum if you were like an oracle who could just, you know, top down Soviet style economy, set everything to the perfect answer. Of course, you can't, but if you could, and then compare that to a system where localized agents made their own decisions and they come to an equilibrium. And you compare the social value you get out of the equilibrium state versus the so-called optimum. And that ratio is called the price of anarchy. And there are situations where you could prove all kinds of bounds on the price of anarchy and characterize it and make it better, make it worse, and so on and so forth. So these kind of concepts exist. And if there's any young people in the audience here, I just really encourage you to learn about this. You know, learn about, you know, don't just fix yourself inside of computer science. It's computer science meets statistics, certainly, but economics, and then EE, you know, dynamical systems. They are certainly contributing their part here. Someone said earlier about, I'm just saying that you should take the intersection of these three fields. No, it's really the union, and it really brings in mathematics, and it really brings in the social sciences, it brings in law. When I say an engineering field, I don't mean some kind of little thing. It's really this distributed democratic academic exercise. And it already exists in the real world. If you go to a company like Amazon, all right, they're talking about like some new pricing mechanism to bring some new kind of product out in some supply chain. It's statisticians sitting next to economists, sitting next to computer science, operations research, and legal people, and so on, all in a team working together. What we have not done in academics is realize that that kind of thing is already existing in our real world out there. And we better catch up.
Thank you very much. With that note, I don't want to impose upon you by taking more time. I really appreciate your virtual visit today, and hope not too far into the future to have the opportunity to host you in person here at some point in Ames, Iowa. You are going to be popular. I guess we will host a show here, so we can capitalize upon that. Thanks very much.
All right. Thank you for including me in your event. Thank you.
Thanks very much. Thanks, attendees. At this point, we will conclude this talk.